my lucky tennis ball. If I were to toss it at the wall over here, see how it comes right back? This is a pretty straightforward example of how things work in our everyday world. In classical physics, objects like this tennis ball follow predictable paths. I toss it at the wall, and based on its velocity and angle, it comes right back. Simple enough, right? But what if the rules weren't that simple? What if the ball didn't bounce back in the way that you expect? What if instead of hitting the wall and bouncing back, the ball simply passed right through it?
Yo, what?
Yeah, I know it sounds absolutely crazy, but in quantum physics, particles can just tunnel through barriers that they shouldn't even be able to cross. Like, the barriers were never there. It's like these particles found a cheat code for the universe. So, the rules? Leave them at the door. Welcome to quantum tunneling. Alright, so let's talk about it. Sounds like some sci-fi nonsense, right? But nope, it's actually a real thing. And it's one of those things in physics that's so weird that it has to be the coolest thing you've heard in your life. Let's get to it. In the everyday world, if you were a particle and you hit a barrier, there is no getting past that barrier unless you have enough energy to jump it. You just hit the barrier and bounce off. But in the quantum world, things get a little weird. Particles aren't just little spheres anymore. They also act like waves. So instead of just having a single fixed position, a particle can now be spread out over a range of possibilities, like a cloud. This means that when you hit a barrier, instead of just bouncing off, part of that wave can actually leak through the barrier. The real funny part? Classically, you can't do that. Now, don't get too excited. That doesn't mean that every particle is just going to start phasing through walls. For tunneling to happen, the barrier has to be thin enough and the particle has to be small enough. For example, if you had a barrier that was just 1 nanometer thick, that's 1/1000th of a meter, then there's a good chance that a particle, like an electron, could tunnel through. But if the barrier is much thicker or the particle is any larger, the probability of it tunneling drops dramatically. Like for a particle that's just a measly 10 times bigger than the electron, the chances of it tunneling are almost zero. But when the conditions are right, part of the wave function can slip through the barrier, and there's a chance that the particle will end up on the other side. But quantum tunneling isn't exactly all sunshine and rainbows. As transistors, for example, get smaller, like we're talking really small, smaller than the width of a human hair, tunneling starts to become a problem. So while tunneling is super important for making electronics foundationally work, it's also something engineers need to fight against when they're making smaller and faster chips. It's a bit of a double-edged sword. Okay, so before we jump into all the quantum wizardry, we need to grab a few tools. These are the imports that we use to do all the number crunching and to make our results look fancy. Starting with NumPy, this is our math powerhouse. It handles all the arrays and does the heavy lifting. Then we've got matplotlib.pyplot. This is what turns all of our numbers into actual graphs so we can see what's going on. Finally, FuncAnimation, because what's quantum physics without some cool animations? Okay, let's get to the fun stuff. We need to define our quantum wave packet. This is the wave that we'll send towards the potential barrier, and here it's going to be a Gaussian wave. It's like a nice smooth curve. Think of it like the perfect wave that you would catch at the beach. But instead of water, it's, quantum stuff. Here is where we set up some key grid parameters. N is how many points we're using for the grid. L is the total length of the grid, and then we've got some things like the barrier's position, the wave's momentum, and the width of the wave. It's like setting up a race course. We're defining the track for our particle to zoom across. Next up, we create the grid where our quantum wave is going to live. Then we define our wave function, psi0. This is the shape of our wave, kind of like plotting the height of a wave in the ocean, except with way more math and way fewer surfers. So self-x here creates our grid of positions. It's like plotting all the spots on a map where our wave might hang out. Self.dx is just the distance between those points. And then psi0 is our actual wave function, a smooth curve shaped by the Gaussian formula with a little bit of oscillation thrown in there to represent momentum. Alright, quantum mechanics 101, here we go. We need to normalize this wave.
It's like adjusting the volume on a speaker. Gotta make sure it's not too loud or too quiet, so that the total probability adds up to 1. Otherwise, your math is off, and your wave is just going absolutely crazy. Here, we're using integration to normalize the wave. This ensures that if we were to measure the probability of finding the particle, it would add up to 100%. Because quantum mechanics is all about balance, right? Now, here comes all the heavy lifting, the energy calculations. This is where we find out how fast the wave is moving and how much energy it's got. It's like calculating the speed and fuel efficiency of your car, but in quantum terms. This part calculates the wave's kinetic energy, and using the second derivative of the wave function, basically it's figuring out how much the wave is wiggling across space. It's like checking out how much your car is swerving while it's on the road. Too much swerve, too much energy. Now let's add the actual obstacle. This is a quantum barrier that our wave is going to try to tunnel through. If the wave's energy is high enough, it'll just go over it, but if it's low enough, it's tunneling time. The potential barrier here has a height of V0 and a width of W. Think of it like a wall in a video game. If your wave has enough energy, it'll jump over the wall, but if not, we're trying to get it to just go right through it. Alright, so now we're getting to the real quantum mechanics of this. The Hamiltonian is just the total energy of the system combining kinetic and potential energy. Once we have that, we can figure out all the possible energy levels of the wave. The Hamiltonian is the grand master of energy calculations. It combines everything, and from there we solve for the eigenvalues and eigenvectors. Basically the possible states that the wave can exist in. Think of it like setting up a playlist. Each eigenvalue is a song, and the eigenvector is the kind of vibe of the song. And now my favorite part, the animation. We get to watch this wave packet do its thing and see if it tunnels through the barrier or not. Spoiler alert, it's cooler than you think. We calculate the wave function each time step, and boom, watch it evolve. We're basically creating the animation of a particle doing its best quantum ninja impression. Really, that's what all of this is. With this animation, we'll be able to visualize quantum tunneling and watch the wave of the particle pass through the barrier instead of just bouncing off the way we would expect it to, like the tennis ball did. Alright, so let's see this code in action. I run the code, and in a couple minutes, we get this beautiful graph by Matplotlib that showcases what our quantum wave looks like. Here, instead of just bouncing off, we can see a tiny portion of the wave actually makes its way through the barrier. And that, my friends, is the tunneling effect. Instead of just hitting it and going back, the wave and potential barrier are at a state where the energy perfectly complements each other, and the wave is able to pass through just a little bit at a time. This isn't classically possible, but with quantum physics we're able to see the effects of the electron at the quantum level.
And that's quantum tunneling. Particles just moving through barriers like they don't even exist. Insane, right? I hope this video gave you a taste of the quantum world and how code can bring it to life instead of having to rely on those massive microscopes. If you're into more of this kind of mind-bending stuff, hit subscribe and follow my website for more updates on my future projects. See ya!